Okay, now we're ready to graph our last sample graph that we're doing. So let's look at f of x or y equals x squared minus 3x plus 1, all divided by the quantity x minus 1. So starting with our domain here, we note that x cannot be 1. Does it reduce? You know what? I can't even factor that. Try as I might, it will not give me the right middle term when I use 1 and 1 for my x plus 1 or x minus 1. Now, to reduce, we say no. Intercepts. If I let x be 0, what do I get for y? Well, that'll be 0 minus 0 plus 1 divided by 0 minus 1. So y equals negative 1 is our y-intercept, and we'll graph 0, negative 1. Then next we'll plug in 0 for y and see what we get for x. So, and I'm going to erase because this is going to take some space here this time. So 0 equals x squared minus 3x plus 1, all divided by the quantity x minus 1. As we've been doing, we'll get rid of fractions since we have an equation. And we'll have 0 equals, these divide out, x squared minus 3x plus 1. And we've already commented that we cannot factor that, try as we might. Now, if you don't believe me, I'll show you. We need an x and an x to force our x squared. We need signs alike to get a plus right there. And since our middle term is negative, I'm going to go with negative and negative, and to get a 1, we have to use 1 and 1, no other choice. Checking our middle term, we get minus x and minus x, which is not minus 3x. Okay, so hopefully I've convinced you that we've no recourse but the quadratic formula. So our x equals minus b plus or minus square root of b squared minus 4ac, all divided by 2a. Our a is an understood 1, and a goes here and here. B is the coefficient of x, and that's negative 3. And c is our constant, which is 1. So x equals 3 when we do our double minus, plus or minus the square root of 9 minus 4, all divided by 2. So we've ended up with x equals 3 plus or minus the square root of 9 minus 4, which is 5, divided by 2. Those are our two x-intercepts, one with the plus and one with the minus. So for exact intercepts, we have 3 plus the square root of 5 divided by 2, and 3 minus the square root of 5 all divided by 2 for our x's. Now when I actually get ready to graph, I want a decimal approximation for these. So let's look at how we're going to get that on our calculator. Go to second, quit. And since I have more than one thing going on in the numerator, it has to go in parentheses. So parenthesis 3 plus second square root of 5, close parenthesis for the argument or the 5 that's the square root, then close parenthesis for the numerator, divided by, and since there's just one thing happening in the denominator, I don't have to use parentheses. Now what I like to do is actually write out these parentheses before I start typing so that I'll put them in correctly. And we've got 2.6 to the nearest tenth for 3 plus the square root of 5. Well, I'm feeling lazy. I don't feel like typing that again, so I'm going to do second enter. toggle back into what I've typed and change my plus to a minus for the other value, and I get 0.4 to the nearest tenth. So let's go back to our other screen and write down what we're going to do. For 3 plus the square root of 5 divided by 2, we're going to pencil in that we have a 2.6 here. And for 3 minus the square root of 5 divided by 2, it's 0.4. Okay, so we're going to graph 2.60 and 0.40 when we get ready to graph. Okay, next we'll check for symmetry. So let's get another screen. And our function was f of x equals x squared minus 3x plus 1 divided by x minus 1. And actually that was an h of x. So let's be precise here and have h of x. So for symmetry, I will have a new y if I plug in opposite of x for x. And that's the way I'm going to check for y-axis symmetry. Okay, minus 3 times opposite of x plus 1. In the denominator, opposite of x minus 1. So how does my new y look? Looks like x squared plus 3x plus 1 divided by opposite of x minus 1. That does not equal our original h of x right here, does it? Well, let's check for origin symmetry next. That means I'll plug in opposite of y for my y and opposite of x for x, but I've already plugged in or substituted in opposite of x, so I know what that looks like. So I'm going to copy it from the previous step. And then I'm going to multiply by negative 1 on both sides to get my regular y. And I think I want my negative 1 to go to the denominator. So I'm going to write negative 1 is 1 divided by negative 1. So I now have that my new y is x squared plus 3x plus 1. Distribute my negative 1, and I get x plus 1. And that does not equal my h of x up here, does it? So I have no origin symmetry either, so no, I have no symmetry. All right, going to A for asymptotes. We said x could not be 1. So we have a vertical asymptote where x equals 1 because it didn't reduce away. And then we want to know if it crosses the horizontal asymptote, which we haven't figured, have we? Let's go back and figure that. So let's erase our cross and let's get our y equals next. Our horizontal, or you know what? Remember, we got a slant asymptote a few minutes ago. We could have a slant asymptote. We'll have y equals, and we'll see whether it's horizontal or slant when we get to that point. So let's erase and get ourselves some workspace here. And remember, we divide lead term into lead term. If it goes a constant number of times, then I know I have a horizontal asymptote. But when I divide, x goes into x squared x times. So this time I have a slant asymptote. And I need to actually do the division because I need to know if I have a constant other than 0 right here. Because at some point, I'll get to the remainder, and we already know that it trails off to 0 as x approaches infinity. But we have to know if there's a constant here other than 0, so we will have to do the division. And this division's a little bit longer than the other. when we have a monomial or just one term in the denominator, we can reduce pretty quickly and get it divided that way. This time we're actually going to have to use the division process. So this time I think I'll use synthetic division since we have a denominator that's linear, or x to the first power. So my coefficients of x squared, 1, of x, -3, and my constant is 1. Every power was present, to the second power, to the first power, no x's, so I don't need a 0 placeholder. Run through a +1 when our factor is x minus 1. So bring down the 1. 1 times 1 is 1. Add, we get -2. 1 times -2 is -2. Add, and I get -1. So -1 is my remainder here, and -2 is that constant. So y equals x minus 2 is my slant asymptote. All right, let's get ready to graph then. Moving to our graph screen. Let's graph what we have. We know we have an intercept at 0, -1. We have 2.60 to graph, so 2.60. And we have 0.40 to graph. Our asymptotes, we have a vertical asymptote at x equals 1. We have a slant asymptote at y equals -2. So I'm going to graph the point, y equals x minus 2 rather. I'm going to graph the point 0, -2, and then use the slope as 1 over 1 to get my line. So 0, -2, and then go up 1 over 1, up 1 over 1, down 1, left 1, down 1, left 1, because remember I could also write that as -1 divided by -1 and still come up with my 1 for the slope. So here's my slant asymptote. Okay, I've graphed everything I know so far. I didn't do one thing I wish I'd done on the previous slide, so let's go back. Let's see if it crosses our slant asymptote. If it does cross the slant asymptote, then the y here, x minus 2, will equal the y here. So let's set those equal and see what happens. X minus 2 equals x squared minus 3x plus 1 divided by x minus 1. Then I'll have a little bit more information that I would like to have. Multiply by x minus 1 on both sides. Now remember, since there are two terms over here, you're going to have to put that x minus 2 in parentheses so that you will distribute this x minus 1 to everything over here. Okay, so multiplying here using FOIL on the left side, I get x squared minus 2x minus x for a total of minus 3x. Then last times last is plus 2 equals the x minus 1's divide out, and I have x squared minus 3x plus 1. Okay, do you see that all the x terms match? Let's do this then. Let's subtract x squared and add 3x on both sides and see what it looks like. Those, of course, will add out, and I have a 2 left. These will add out with these, and I have a 1 left. That is always false, so we could not find an x by setting the y's equal, so no, we don't cross the asymptote. So moving back to our graph here, we know we're not crossing the asymptote. So graphing the left side of our vertical asymptote, I think we've got probably enough points just to go ahead and head toward the asymptote. I might feel better with another point on the right side of the vertical asymptote. So let's plug in -2 and get a y to go with that. That's a +2. I'm on the right side, so +2. Plugging in +2, I'll get a -1. So +2, -1. I think since we're headed toward the asymptotes and don't cross them, we're okay. And there is our graph here. That was kind of a long one, wasn't it? We had a slant asymptote that had a constant other than 0 in it, so it took us a little more time to even find that asymptote. Next time, we'll look at an application of rational functions.